Welcome to another physical sciences lesson. Today we're going to look at chemistry, specifically at the rates of chemical reactions. We will be investigating the rate of chemical reactions. Now I want you, while we're going to go through this lesson, I would like you to think about this question. Why do older cars sometimes take a long time to start on a cold morning in winter? I would like you to take some time during this lesson to see if you can answer this question. Now, I'm going to take you through the concept map so that you can see what we plan on doing during this lesson. So, firstly, I would like to go and look at the definition of, I would like to look at the definition of rate of reaction, and then we will link that definition of rate of reaction to the factors affecting the chemical reaction. Now, when we look at rate, as I said, we think in terms of some of our reactions take longer and some of our reactions are very short reactions. And looking at the factors at a later stage, we will be able to see how we can alter to make a reaction faster or to make the reaction slower. The terminology that's important for this lesson is words like reactant, the substances that we need to start up a chemical reaction, words like product, the substances that are formed, and then the yield, how much of the substances are converted into a new substance. So, as I said, we will look at reactants, products, and yield, and these words or terms will be used a lot. When we look at rate of reaction, I said to you that the rate of reaction is how fast or how slow a reaction is. Now, if we're going to look at just how fast or how slow the reaction is, there's also in the guidelines document, there's a definition that you must study for your exam. And that definition says that the rate of a reaction is the change in the amount of your reactant or product. So you can decide whether you will take the reactant or whether you will take the product, but what's important is you must know that that rate must be per unit time. So whenever you answer anything on rates of reaction, you need to refer to per unit time. In that way, we will be able to see how slowly or how fast a reaction goes. Here I've got a slide on fast reactions. If we look at these three photographs here, we can see combustion, we can see explosion. Now, when we look at fast reactions, as the word says, it's a very quick reaction. It happened over a shorter time. So, fast reactions are normally exothermic reactions, and with exothermic reactions, what's important is the energy that we need, that needs to be absorbed for the bonds to be broken is less than the energy that is released during these reactions. On the next slide, I will just quickly talk about activation energy. Now, for every reaction, there is a specific activation energy at a specific temperature, obviously. But the definition for activation energy is one of the terms that we need to understand in order for us to go on with rates of reaction. Right. So your activation energy is your minimum energy that is needed for this reaction to take place. We use the symbol E with a subscript A for activation energy. And as I said, it's the energy that breaks the bonds of the reactants, and that reactants will form new substances or products. So the bonds must first be broken in order for the reaction to proceed. And at the point where the bonds are broken, it means that we have sufficient activation energy for those bonds to be broken. Right. In front of us, we have now 3 pictures of slow reactions. Now, slow reaction will basically mean that the time for this reaction is longer. And what came to mind is the baking of bread, where we use yeast to get the bread ready, but it's not ready immediately. It will take an hour to 2 hours. If you look at rusting, rusting happens over long times where your iron, for instance, are exposed to oxygen and some moisture in the air, and that iron will then rust, become brownish on the outside. It's a very slow reaction, but it does happen. When we look at another reaction is, for instance, the fermenting of fruit cells or fruit juices to make wine. When we look at our slower reactions, as per our faster reactions is normally exothermic reactions, where the energy that is released are much higher than the energy absorbed. But when we look at yeasting, for instance, if we look at the energy profile here, we have an endothermic reaction. And again, the energy absorbed for this endothermic reaction is then bigger than the energy that gets released during this reaction when the products are formed. Therefore, it is an endothermic reaction. Right. And we now spoke about the profiles of the energy. We know that energy needed, minimum energy needed to break the bonds, to form new substances. These substances are called products. To break the bonds, we will see color. We will see the reactant get less on a scale. Therefore, we can say on a macroscopic view, we can see certain things. We can observe a color change. We can see that the temperature is changing if we use a thermometer. So on a macroscopic view, we are quickly going to look at the 6 factors that has an effect on the rate of the reaction. These 6 factors, if we look at number one is if I change my temperature. If I look at temperature, I want you to remember that temperature is a measure of the average kinetic energy of a substance. So if a substance has got a high or is exposed to a high energy, it will have a fast reaction. And that fast reaction, we will refer to it as having a high rate. But that fast reaction have got a low time frame or a small time frame that we're talking about. So if your temperature is high, you will have a fast reaction and a high rate. If we look at the opposite, where your temperature is low, you will see that the reaction to form your product will take a much longer time, and we refer to that as being a low rate of reaction. The second one that we're going to look at is the surface area. Now, when we look at surface area, I want you to think in terms of solids. So when we look at solids, when we talk about a large surface area, we talk about small particles. For now, I'm just going to say we will look at powder. So when we have a powdered surface, we will have fast reaction, and we will say it's got a high rate, and this fast reaction will happen in a very short time frame. When we talk about a small surface area, we talk about large particles, and what I can draw here for us is a piece of magnesium ribbon. Now that magnesium ribbon makes up a large surface area. That are the first 2 that we spoke about. A change in temperature can alter the rate of reaction, or it can influence it. And surface area, if it's a small or a larger surface area, that's got an influence on the rate of the reaction. Another factor that I want us to look at is, what does concentration do on a in the macro view? the macro view, we know that concentration, according to our chemistry formulas learned to date, is the number of moles per volume. So if there's a high concentration, because concentration is directly proportional to the number of moles, it means that a high concentration will have a high number of moles. That will have a fast reaction, high rate, meaning in a small time. Low concentration means there will be a low number of moles and it will go for a slow reaction, and a slow reaction happens in a longer time. The fourth factor that we're going to talk about today is pressure. But when we look at pressure where we use gases only. And the gas must be part of your reactant, not necessarily part of your product. So when we have a high pressure, we have a fast reaction, a high rate of reaction, and at a low pressure, we have a slow reaction and a low rate, meaning longer time. Then catalyst. When we get to catalyst, firstly, I would like to say that a catalyst is a substance that can have a positive or a negative influence. It can make a reaction faster or it can make a reaction slower. So just to look at catalyst, catalyst is a substance that changes the activation energy, and when this activation energy is changed, it is not used up during the process. So it does not take part in the reaction. When we look at positive catalyst, a catalyst that will speed up, it makes the reaction faster, but it makes the reaction faster by lowering the activation energy. So it makes the activation energy lower, makes the reaction faster, and it is then a high rate. Now, I just want to show you the energy profile where we put in a catalyst to show you what we mean by saying decreasing or lowering the activation energy. In front of us here, we have an exothermic reaction, and for this exothermic reaction, we can see that our delta H is negative. So what I want us to see is, under normal circumstances, we would have needed that activation energy for this reaction to take place. But when we have a positive catalyst, we now lower the energy to a point where we only need that amount. So if I can draw it like that, you will see it looks as if this reaction can take place so much faster. Negative catalyst does the opposite, meaning it increases the activation energy, and when it does that, it actually slows down the reaction, slows down the rate of the reaction. Then the very last factor that I want to talk about is, and this factor we don't talk about a lot, but it is a factor that needs to be taken in consideration, and that is the nature or the type of reactants that we use. Now, some of our group 1 and our group 17 elements, when they react, they are very reactive. Not some of them, all of them are very reactive elements. They make for a fast reaction, high rate reactions. But if you look at your inert elements like nitrogen, gold, platinum, they don't really want to react. So when they in a reaction, they have slow reactions, low rate, meaning it takes long times for these reactions to take place. And this brings us to our first break. See you just now.